Good morning everyone, welcome to Liquid Brain. So today I want to show you how you can actually run your own RNA-seq workflow from your raw FastQ file, map to the transcript, generate your BAM file, count matrix, and identify a DEG from two different samples. So before we start, you will need R installed on your computer, version 4 and 4.0 and above. You need 3 packages mostly, Rsubread, DeSEQ2 and Annotating. You need a reference transcript, you need read 1 in FastQ, read 2 in FastQ, and you don't have the reference and reads ready on your computer, you can use the sample that is attached with the packages, so don't worry about those two. And finally, RStudio or any IDE of your choice. So again, disclaimer, this is not me going through a real research data set. This is a stringed down versions of the sample file that I find based on the tutorial from other authors. I will credit them, and their original content and documentation will be in the video description below. And if you're gonna run this on your own computer, just understand that the mapping and the generation of BAM file actually takes a lot of hard drive space, and it might actually take a lot more RAM for the building of the index and the mapping situation. And I cannot confirm that you will be able to run this on your own computer. But it's also very important to understand how is it done and why is it done a certain way, so that when you're writing your paper, you understand what is expected. So I want to go through 4 different things over here. So the first package will be Rsubread, which is kind of a mapping and counting library where you can load your reference genome, you can log your reads, map it, and generate how many counts is it per gene location. And then we're going to load that count table into DeSEQ2 and run some basic exploratory data analysis based on the differential gene expression list that we have actually fished out. So it's not going to be much because we're running on reference data here, and we'll see what happens later. So the first thing first is to go to your R and actually just open the code. I would suggest you to go to my GitHub page and download the whole folder. So when you open, you already have all the global object already loaded into your environment. Okay, but the first thing first is to install Rsubread. So if you're not familiar with bioconductor installation, you just install the bioconductor package first, and then run a BioC manager install Rsubread to get the library. So first thing first, always insert the library. Let me see if I can make things any bigger. I don't think I need to. 150%, perfect. Okay, so first thing after you have actually installed, load in the library for Rsubread is to actually tell the package where is the location of the reference on your computer. So we're using a system file, which is one of the reference FASTA file from the package Rsubread in the folder called ext_data. Actually, you can have a look at the overall, what is that called? Overall directory of the file in your own computer, and yours is going to be slightly different from mine, but the code should still work the same. So once we have loaded out, you actually build an index. So what's the meaning of building an index? Is actually just creating a hash table that is, I will just understand it as it's easier for us to map it later, it's more efficient and it's faster. Okay, so if you do not want to use the reference FASTA file from the package, you can also choose your own. Just insert your file directory here for the reference, and insert your file directory here for the reads that you're going to load into your own environment, assuming that you have a very powerful computer and a lot of storage space and a lot of RAM for you to run. And of course, it depends on how big is your reads. So many factors over there. So similar with the way of how we import the reads. And now once we have the reference index done, we have the reads index done, we're going to do an align. So they're going to align to an index, which is the one that we have built earlier. And this is going to take a little bit longer than the one just now, because aligning every single one to every single one is kind of a difficult task. And even though the reads and the reference fast out here is only 80 kilobyte, it already takes a minute or two for the mapping to happen. Okay, so we are using a thread offset score of 64. You can think of it as when you do an RNA sequencing, every single base pair has a quality score. So this is one of the quality score that we do, and you can choose different file based on your sequencing quality. And if you're running something like a preserved sample, of course, your quality might not be as good as a fresh sample, and you can adjust a little bit based on that. And it's also going to generate an output file called alignresult.bam. So this will be the BAM file that you will be able to know what is the mapping result. So if you want to know more about the BAM file and SAM file, you actually did a video about that, which I can link somewhere on the bubble, hopefully. Okay, it's still gonna take a while. So after we have done the alignment, it should generate all this thing, which again, we're gonna do another alignment using two different reads. So just now we only do a single reads over here, and now we're gonna run another read, the same process basically. And we're just gonna run a separate read so that we have two aligned results. Okay, we are done. So we have basically aligned two different sets. The first step is actually just a single read file, and the second set is actually two read file. So we have what this basically means is that this is a single end sequencing result, and this is a pair end sequencing result. So what I usually tell people is that if you are very familiar with the sample and you can get consistent result and you have enough replicative data, single sequencing and usually it's fine. But if you're doing anything that is new that you don't really understand or you've never did it before, pair end kind of generate a little bit more of a peace of mind that you'll be able to cover out more coverage of your genome. So we can also see that the output file is slightly different. There's a alignment result PE as output file, and this is align stat 2, and the first one align stat 1, and the align BAM file is just align result.bam. So a little bit of difference in the BAM file over here. Okay, so the next one is going to build is the annotation table. So this is a dummy annotation table, which actually have like, this is the gene location, this is the chromosome, and this is the start and end, and this is the strand positive and negative. So in reality, when you actually load this table, it should have the correct ensemble gene ID, the chromosome 1, 2, 3, 4, 5, and every single of the gene location. So when you actually map it to your proper location, actually you'll be able to actually see what is the name of the gene. For this case, we're just gonna use it as an exercise, but you can change the annotation to your gene annotation table, and this should be fine. And I believe you can actually download this file somewhere on Ensemble. So I'll try to find a link in the video description if I can. And the next one we're gonna run is a feature count. So feature count, very simple. You just count whatever gene is appear on the same location. So you can have a look over here. This is the single end result. So what we are interested in is actually the count data. Where are you? Yeah, this one. So this is the gene number, this is the length, this is the statistic, and this is the thing. Okay, it's not here. So yeah. Oh yeah, it's here. Okay, so it's the count. So you actually need to go for SE count, something like that. Okay, so this should give you the result of this count table, where you have the alignment result.bam, which is actually they count it from the BAM file. You have gene 1, gene 2, and it appear 14 times and 70 times. So if you go back to the annotation, you can see gene 1, 2. This is the location of the gene, and this is the location of the gene 1 and gene 2. Okay, so again, we can do the same thing with our pair end result, which actually you can again see that on the count here. Okay, you can see that 16 and 19, obviously, because they are pair end and they cover a bit more coverage, and you actually get more count. But usually they'll be in the correct ratio, something like that. Okay, so once we are done, actually we are done with the import of the library, import of the reference, build an index, mapping, and actually got the count result. So once you get these two, you're practically ready to go for our next steps. So we have load the reference, build index, import reach, and map reach to reference, and generate the count table. So now we actually need to to import the two count table into DeSEQ2 and run a simple differential gene expression analysis. So with the magic of, with some movie magic, we're not actually going to use the result that we generated just now, because we have two samples and each of them only have two genes. We're not going to do anything significant with that. So I'm going to actually use one of the library, and we're going to use the data from one of the previous experiment, which is slightly bigger, and you can see some of the difference between. You can actually see some different gene expression and some of the MA plot that we have later. So here I'm using a library called parathyroid SE. So this is actually an experiment from the parathyroid genes. So the previous experiment on parathyroid. So we're gonna also use the function called data, where actually we'll pull the data of I believe this is an SE object. Yeah, this is an SE object. We actually contain the experimental data, their count matrix, as well as their annotation. I believe this one has no, they have annotation, something like that. Okay. So first thing we do, if you want to run DeSEQ2, you have to load the DeSEQ2 library into your environment. And assuming that you're using your own count matrix and not directly load it from a sample data, you can actually run a dummy count data over here like that, so that you can actually see that you see our dummy count matrix. You go to dummy count matrix, so you can use this directly to load into your DeSEQ2 if you are running your own experiment, assuming you have more sample and more gene. So with a count matrix, if you have more sample, add it vertically as a column, more gene, add it horizontally as rows. Okay, sample, genes, and exactly like that. Okay, and you can just load it as a data frame and you can load it in later. But here I'm just going to use the parathyroid SE, and we're going to build our count matrix, which is something like that. Okay, so you have the row names are on as the gene ID, and V1 to V27 over here is our 27 samples. Okay, and so we have 27 samples. We also have to define what our 27 samples are. So we're going to use a function called column data to pull the column data from parathyroid genes SE. So just to visualization purpose, you can also convert that object into a data frame which I call experimental data here. So if you open experimental data, you can see that we have 27 rows. So 27 rows means 27 sample, and every row will contain all the detail of each of the sample. So in this case, this is patient 1, control, time point 24 hours, and so on. And sample 5 over here is treated with OHT at 24 hours. Okay, so yeah, so we have row names, and the next one we have row names. So before we actually build it into a DeSEQ2, we need to ensure that our count matrix and column data are able to match back to each other. So what we need to do is that for our count matrix, we cannot use V1 to V27. It wouldn't work. They don't understand which is which. Same with experiment data, we cannot go for row 1 to row 27. So these two just convert your count matrix. Not yet. So this one convert your column data properly. As you can see that, our column data, and we convert the column data into experiment data. As you can see now, our row number has been changed to our sample name. And then next one, we're gonna rename our count matrix, which have our proper name as our columns over here. So that when you load into DeSEQ2, they know how to map the two data frames together. Okay, so the next one is to create a DeSEQ object. So it's called DDS full count table. So this will actually just tell the DeSEQ2 command, this is our count table, this is our column data, and this is our design. And here we are only gonna use treatment, though. So it depends on the experiment design. So what this means is that your independent variable is your treatment, and your dependent variable is your count number. Okay, so of course you don't just have to have a single treatment. So if you need anything, you can just add. Let's say I want to add time plus treatment. So you can also do that. And next one, we're gonna run DDS. So estimated time size factor, estimate dispersion, gene-wide dispersion estimate, and this is also gonna take a while because I have to calculate how many genes do we have? 63,000 genes. Okay, now we're done. So now we have fully calculated all the object and we have generated a new object, a large DESEQ2 object. We can see here DESEQ2 dataset, and we have our design formula, dispersion function, row range, assay, and so on and so forth. Okay, so now it's for us to have a look, how does our calculation looks like and is the data able to be used. So the simple way is to just filter away on log2 fold change and send to your customer, and you're gonna die. So a lot of time we need to do a lot of pre-processing before we can actually finalize our count data. So the first one is actually called a dispersion plot. Dispersion estimate plot. Okay, so what does this do is that it will create a figure of two axes. So the x-axis is the mean of normalized count. So what does that mean is that the higher the number, the more this gene is being found in your sample. This could be something like housekeeping gene, like actin, which is expressed all the time. While if you have something lower on the count, it could be something like a transcription factor, which are not as frequently expressed as the housekeeping gene. And we go on the y-axis, which is the dispersion. So dispersion, as the name is, how wide this is being spread within the sample or within the different sample that we have. So it is normal that for a lower number of count, because you have smaller number of gene being expressed, the variability or the dispersion between the sample is going to be bigger, and the dispersion is going to slightly goes down as the size increase. So what does this dispersion do is that you apply something like a correction factor, which is actually, as you see the fitted line over here, so that it will actually recalculate some of the thing up there, the black one, so that it's actually fit better with the dispersion rate, and this should improve the it should increase the accuracy of the estimates for gene that are slightly on a normal count number and dispersion. So for example, if you have more dispersion of a certain gene, the log fold change need to be bigger for it to justify it as a DEG, as compared to some gene which doesn't have big of a dispersion. Okay, so once you're done with this, okay, this is a very good plot. This is what is expected of the RNA-seq result. However, if you have like a red line that go like that up and down, there might be contamination. You have a large number of black plot, you might have contamination. We don't know what happened to the experiment design. You might have renamed something wrongly, we don't know. Okay, so but if you see something like this, most of the time you are safe. Okay, so to actually get the result of your DESEQ2, you just use the result function, and you can actually just run the result function over there. So yeah, so what you're interested in is the list data, and you can actually see that these are the base mean, and there's the log fold change and p-value and so on and so forth. Okay, p is just very high. Might not be a good thing, but it might be because of experiment design. We're gonna explore that later. Okay, so yeah, so this is what we do. I'm gonna use a data frame list data to put a data frame result, so we can have a better way of understanding of all the log2 fold change and p-value. So we can actually sort by our p-value and p-adjusted. Our p-adjusted is very high, so this is kind of a problem, isn't it? Okay, but our log2 fold change, you can actually see there's a significant difference among a lot of them. But of course, you're not going to scroll through 600 different rows of data, right? So even though I can just put in the gene name, it's not a realistic way for you to visualize your overall result data. So MAplot in this case provide a very good way of visualizing your whole the comparison between your two samples. So again, we have the means of the normalized counts on the x-axis, which is on the right, means they express more in the cell, less they express less, and we have the log fold change over here. So anything that is positive means they have a 3-fold increase in the count number. Okay, a higher number they express more, minus they express less, and it's usually calculated in log2 because it's more easier way to understand fold change. Okay, so you also will expect to see something like a diamond shape over here, and if you have a MA plot which the tail slanted to one side, that's usually non-desirable. Means your plot might not be properly normalized, and you might want to look into what is the situation over there from your experiment. It might be correct, it might be wrong, depends on the interpretation and the experimental design. But usually we want it to look this way. And next one we're gonna, this is the one that is usually scary. We're gonna filter based on our p-value and p-adjust. So if you look at our p-value, and if you want to use a cutoff of 0.1, just not that bad. We have about 5 to 10% of DEG. But if you actually run on a p-adjust, you realize that, oh, everything is 1, so nothing is significant in our result. And this is the time where you kind of go and cry in the corner, and we just not gonna look at it again. But it could be something wrong with the experiment design. So let's change a little bit of what we do on analysis over here. So in result 2, we're gonna put another thing called contrast. So what does contrast means is that when you do like what we do in the result just now, you're just comparing all the treatment and all the time together, and it might not be correct. So we're going to put a contrast in. So contrast is just that you only want to compare the two results. So let's go our experiment data. So in our treatment column, which is actually the first argument over here, we have only OHT versus control. So now we're ignoring the DPN, but you still have the time frame here, which might be the problem. So we only want to control the DPN versus DPN versus the control. So we don't want to compare DPN. We want to throw DPN out of the question, and we only compare OHT to the control, and we want to see what happens. So let's try that. So let's go for MA plot, and it's kind of very similar to what we do the rest. Let's run our histogram again. Yep, we got no result. So summary, the outlier 171% doesn't work. So what we could do further is actually apply a string. So what does a string do is that it will actually look at not the dispersion, the variability between the sample size, and try to apply kind of a correction factor, and then in theory, without going in deep into algorithm, it will increase the accuracy and the discoverability of gene with a lower count rate. Okay, so you go here and you actually need to go to result name and see which is the one that you want to compare, because we do put a time just now versus the treatment. So actually these are actually included in part of your DDS just now. So here we only want to do which one is the one I want to do? I'm completely lost in my thing. Is it here? String. Res2 is now we're on Res3. Okay, so we're on a string, correct. So coefficient, once you run the result, you want to run which coefficient do you want to run? So is it 1, 2, 3, or 4? Let's say I want to run 4 this round. I want to see what happens. So wait, you have to run the 4, because this is the Res2. Res2, you kind of have to run the same coefficient that you run over here, and let's see what happens when we plot a string. Okay, so it's also using APEGLM, which stands for approximate posterior estimation for GLM coefficient. I'm not going to talk about it here, but if you do want to read about more, they do actually provide you a link for you to understand the detailed algorithm on how the string case actually works. Well, there's going to be a lot of cut in this video, isn't it? Okay, so now I'm back. So let's say I'm back. So now we are done with the string. Let's do a plot MA and see what does our string result actually indicate. And indicate that we have no log fold change and we are completely gone. So it doesn't work as well. So string doesn't work for this result analysis. So let's try again with a different alpha, and we run a different plot, MA plot, which is unlikely gonna make any difference. And it doesn't make any difference at all, so it doesn't work. Okay, so now it's kind of a point that you maybe want to rethink your life about your experimental design, or it might be very good for you because your treatment doesn't affect the cell and it might be safe to use. So it depends on what you are looking for. Okay, so once we're done now, we'll assume that everything works fine and we're not going to drill down into further analyzing the experiment. We're going to do it in our next video. So we're just going to export the annotation result to our client, let's say. So we're going to use a library called Annotable over here. So this is actually a self-maintained package. So you might want to go into dev2 install GitHub. And actually this is from Stephen Turner. So just install Annotable from there. So once you're done, is where I'm going to load the annotation table from the object called grch38. So it's grch38. I usually like to do that so that it appears on my environment over here. So what it has is that it has all the ensemble gene ID, the interest, symbol, chromosome, start, end, strand, biotype, and description, and so forth. So when you're doing your mapping, you could actually just use this as part of your index just now. Where is it? Yeah, annotation table just now. So when you map it, you should be able to get your annotation result directly if you need to. Okay, so once we are done with that, we're just gonna do a subset where we use a p-value instead of the p-adjust so that we at least get something. And we can just rename the column and we're gonna do a left join from the DEG result and our annotation result and merge them together. So this should result in a table that looks somewhat like this, where you have the ensemble gene ID, the mean change, the statistic, p-values, and just keep the p-adjust in and hope that they don't find it, and interest, symbol, chromosome, strand, biotype, and description. Okay, so you can again filter by biotype, you can again filter by description, and so on and so forth. So this is what you usually receive from your servicing company, let's say. Okay, so the last one, we're just gonna write a CSV as a CSV file, and we're just gonna send it to whoever that needs it for the downstream analysis. So as you can see from our experiment data, we only consider the time and the treatment, and you might want to further experiment on the patient, the treatment, the time, and we might want to subset a little bit and compare the different patient and how they react, the different treatment or what they had and time on what they have on the patient, because there's obviously different factors here that we have not analyzed. But the video is already half an hour long, so I do not want to go on further. I'm going to split those downstream analysis into a separate video. It's coming out later, hopefully. Probably, I decided. But for now, let's do a recap of what we have done today. So what we have done today is that we have used two packages in R. We load Rsubgene into, we use the Rsubgene library to load the reference, build an index, and then import the reads and map the reads to the reference. So for those that wants to use your own sample to run this experiment, where's my file? I lost my file. How did I how did I lost my file? That's impressive. Okay, so for those that actually want to use your own file, you can just change whatever reference directory to your own reference directory and change the gene directory to your own directory. And you can use the Annotable to load in as your annotation, so you get a full count table directly. You can also do it on Galaxy. There's also slightly easier way to do that. And once we've done the mapping, you should actually get a BAM file, which we use a BAM file to go into feature counts, and the feature count will give you a count matrix. So once you're done with the count matrix, we're going to load the count matrix and the column data, which is actually your experimental data. So this has to be supplied by you because that's how you prepare the sample, and we load these two into DeSEQ2. So once we load into DeSEQ2, we just run a DeSEQ2, which will actually calculate all the DEG and log-fold change for you, and p-value and p-adjust for you directly, easily. And then we do some exploratory analysis with like plot MA, dispersion plot. We run a bit of the contrast here and there, and we actually how to join the data later with the annotation table. You do not need to join the annotation table if you are running in the beginning where you build the references. So hopefully that is able to help you to run your own bioinformatic analysis. If not, at least understand that how it could be run, and when you interpret the result, especially when you look at the p-adjust and p-value and what would be the significant difference that you have. And when they give you something like a dispersion or MA plot, what does that mean and what does it do to your result afterwards? So that's it for now. I will try to do another video on this with more deep dive into the experimental design for DeSEQ2 and try to actually get a narrative out of that, which they already does on the paper. So with now, thank you for watching. I hope you learned something and we'll see you into the next one. Goodbye.